This video shows how to solve linear systems of inequations and is part of a set of videos that also include a complete system of inequations, the compatibility of these systems, and applications to linear programming. The solution to these problems is difficult or impossible to find in the existing literature, in spite of its great importance and practical applicability to real problems. In particular, we know that when the solutions or the feasible sets are known, solving linear programming problems becomes trivial, and then their solutions can be immediately obtained. This slide shows a set of homogeneous linear system of inequations, which is written in the traditional form. That is, it highlights the linear combinations of the unknowns, as shown in the slide, which must provide the values in the right-hand sides. We normally write these systems in this form. However, to discover the structure of the set of all solutions of a homogeneous linear system of inequations, we need to write the system in a different way that allows us to discover this structure. I usually say that for this to be possible, we must put on different glasses. That is, the system must be seen from a different point of view. This is precisely what the system in the lower part of the figure shows, which is exactly identical to the previous one, but which, being written precisely in this form, shows us the structure of the set of solutions in a very clear way. As we know, the scalar product which appear below of the vectors of the coefficients of the equations above by the vector of the unknowns are precisely the linear combinations of the equations above, what proves the equivalence of both representations, that is, that both systems of equations are the same. Anyone who knows the definition of a dual or polar cone immediately identifies these sets of solutions as the polar cone of the cone generated by the row vectors of the coefficients of the inequations in the above system. Therefore, this shows that the set of all solutions in the system is the indicated polar cone. Thus, the problem reduces to find the polar cone of this cone. To obtain the dual cone of a given one, we use the Joubert-Gamma algorithm, which allows us to give the initial cone as a cone or in its standard form. But the generators need not to be neither linear independent nor the edges, and any set of generators can be used. In addition, the dual cone is given in a standard form, that is, the bases of the vector space and the edges of the acute cone are given if they exist. Therefore, the most compact form of the dual cone is obtained. It should be noted that the dual cone of a given cone can be obtained by means of an algorithm that we have implemented as a web page in JavaScript, which can be accessed through the following link. In addition, the following link shows a video explaining how to use this program. This can save you a lot of work and errors, so I recommend you to access this application, which is free. This algorithm provides tables that give you the dual cone of a given cone. Each table gives the dual of the cone generated by the vectors introduced in all the previous tables. Therefore, the finite table contains the dual cone of the initial cone. As indicated, the dual cone is given in standard form, that is, in its simplest form. The following slide shows an example of a homogeneous system of inequations written in the traditional form and in the proposed form, which allows us to say that the set of all solutions of the system is the dual cone of the cone generated by the vectors of the indicated matrix, which contains as columns the vectors or the coefficients of each inequation in the system. The following transparency shows the tables corresponding to this example, obtained from the web page application above mentioned, showing in iterations 2 to the finite table the dual cones of the cones generated by the first 2, the first 3, and all of them, the latter in the finite table, which in column V it contains the basis of the vector space part of dimension 1, and in columns W the edges of the acute cone part of the dual cone. Therefore, we can write, as it appears in the lower part, the solution of the system are the sum of a vector space of the dimension 1 and an acute cone generated by 3 edges. We know that the subscript in the matrices, the Greek letters rho and pi, refer to linear and non-negative combination respectively. Developing this expression, we obtain the set of all the solutions that are expressed as a function of a coefficient rho, a real number, and 4 coefficients pi, non-negative real numbers. Finally, it is interesting to replace these expressions of the unknowns in the equations of the initial system and check how they are satisfied, regardless of the values of the rho and pi coefficients. It is interesting to indicate that what will happen if the inequations were strict in one or more of the inequations. In this case, the lower part of the tables tells us which coefficients are subject to being non-zero. In particular, the coefficients associated with vectors in which the number of the strict equation does not appear in the lower part of the table could not be simultaneously null. For example, the number 4 does not appear in the sets associated with the vectors w1 and w2 of the finite table, so pi1 and pi2 cannot be simultaneously null if the inequality of equation 4 is strict. Finally, it should be said that because the dual cones of the cones generated by the first k inequation for any k value of the system appear in the intermediate tables, 4 different systems have been simultaneously solved, as shown in the table, which shows the solutions of all of them. Finally, we provide an illustrative example of strict inequalities. Consider the indicated system of inequations, which is the initial one, where the less or equal relations in equations 1 and 3 have been replaced by strict relations less than. Replacing the previous solution into the initial system, we have obtained the inequations 1 to 4, which imply that neither the pi2 and pi4 nor the pi3 and pi4 coefficients can be simultaneously null, because the relation less than 0 in the system corresponds to inequations 1 and 3. Thus, the solution of the given system of inequations above is the previous one, but in this case neither the pi2 and pi4 nor the pi3 and pi4 coefficients can be simultaneously null. To find the pi coefficients involved in each inequation, we do not need to replace the general solution into the system as above, because the lower part of our table, which contains the indices of the generators of the initial cone, which are orthogonal to the corresponding v and w vectors, contains this information. To this end, we take one inequation, for example the first one, and find the column w vectors in the table such that the index of the inequation, in this case 1, is not contained in the set of indexes below the vector. The 1 is not contained below vectors w2 and w5, which have associated the pi2 and pi4 coefficients, which are the pi coefficients appearing in equation 1. The reader is invited to solve the same system by replacing other less or equal relations by less than relations. With this, we end this first video dedicated to system of linear inequations. We invite you to see the next videos dedicated to non-homogeneous system of linear inequations, to compatibility conditions of these systems, and to linear applications to linear programming, which not only are solved very easily, but also, contrary to most linear programming solvers, supplies all possible solutions of the given linear programming problem.